So welcome, everybody. We have Seth Pevarnik, Director of Technical Services and at Ardex Americas, working with Ardex Americas in the Technical Service Department since 1991. Seth leads the Ardex Academy training program. His areas of expertise are concrete, moisture in concrete, proper substrate preparation, underlayments, toppings, and decorative applications. He has been certified in substrate and subfloor inspection, as well as substrate and subfloor preparation. Seth is active in many industry associations and standards organizations, including ASTM, FCICA, StarNet, Install. I'm going to add NFCA as another acronym to your files.
Absolutely.
And is currently chair for as the IICRC chair for the ISSI certification. ISSI stands for Introduction to Substrate and Subfloor Inspection. So there's all sorts of certifications and learning you can get, good quality learning on this contentious topic. Truly, Seth, you are the meat in the sandwich somewhere between flooring and the parent concrete surface. So yeah, tough job, and we're very happy to have you here. So please continue, and we're looking forward to it.
Yep. Thank you very much, Chris and Lee. I appreciate the opportunity to spend a little time with everyone here this afternoon, talking about causes and remedies of concrete slab imperfections. As Chris said, my name is Seth Pevarnik. I'm the Director of Technical Services for Ardex Americas. Okay, so what are we doing today? We got a lot on our plate, a lot of good stuff, but we'll review joints and cracks. We're going to talk about a process called slab curl relaxation. We will address pop-outs and blisterings of concrete to include osmotic blisters. We'll review alkali silica reaction, that's also referred to as alkali aggregate reaction or near surface aggregate reaction.
Yeah, I understand that. I just don't do water damage anymore, Gene. I just don't.
Oh, you don't?
No, you got hard surface in the basement, you got carpet.
Carpet and
Can we please ask everyone to mute?
Okay, can you hear me, Lee and Chris?
Yes, we can. Thanks, Seth.
Good deal. Thank you. So some of the other topics that we'll address, spalling of concrete, scaling of concrete, dusting, a very difficult word in that it's called efflorescence, condensation. We'll look at pH, fly ash in concrete, and then the correct way of harvesting samples if that needs to be done on a specific project. Okay, so we're going to start off with joints and cracks. We certainly see these in all concrete. There's control joints that we'll discuss, construction joints, cold joints, and you have expansion joints which are moving, isolation joints that are moving, and we'll wrap it up with crack preparation. So two classifications of joints and cracks that we see in concrete. First category called moving, sometimes referred to as dynamic cracking or active cracking. Certainly an expansion joint is a moving crack, or a moving joint. An isolation joint is also moving. You know, these are designed to allow movement between concrete slabs or between concrete and a structural concrete caisson. Construction joints where we pour concrete today and pour concrete tomorrow, sometimes referred to as a cold joint, moving. Structural cracks are usually moving as well. These are the ones that are typically identified with vertical displacement, and I'll show that in a future slide here. Some of the non-moving that we see out there that are also referred to as static or dormant joints or cracks. Number one, control joints. Control joints or the saw cuts. We'll address this. And sometimes you see crazing cracks, or they're called old craze cracks. And that's when we'll address this as well, but the surface of the concrete dries out and it can create a crack pattern that looks like a map. but that happens during the drying process of the first couple of days and is typically not a moving crack by any means. So, control joints, also known as saw cuts or even referenced as contraction joints. Concrete binds, roughly 30% of its water, maybe 33% of its water, and has to evaporate, 63 to 65% of its water, something like that. That loss of water equates to loss of volume. And when you have loss of volume, something gets smaller, something that gets smaller, shrinks, it cracks. We know this with concrete. They cut joints into the concrete called control joints to isolate the shrinkage cracking to the base of that saw cut. Okay. What's very commonly done, as seen in the picture on the left with saw cuts, is they're patched with a floor patching material, and then floor covering is installed. Commonly done, day in, day out. However, just because you patch a control joint does not necessarily mean that you never have movement and never see that joint telegraphed through a floor covering. And I bring this up because I want to talk to you about a condition called slab curl relaxation. Okay, and it's two parts here, and I have a slash between them because slab curl is one thing where the edges of a concrete slab can curl and the edges are raised, but the relaxation is another function of this of a certain situation here that we're going to talk about. So it's slab curl relaxation. So the bottom line here, with concrete slabs that are on ground with a vapor retarder directly underneath of them, can experience slab curl due to differential drying. And what I mean by that is if you have a vapor retarder under the slab, which is recommended for any moisture sensitive flooring, it's going to go on that concrete. The mixed water in the concrete, that 65% of the mixed water that evaporates out, is not going to go down. It only goes up. And if it can only evaporate up, that differential drying can create a slight curl at the joints, at the control joints. And the quickest way to see if you have any curls, just take a straight edge, take a 4-inch straight edge and go to the joint and place it over the joint. And if it's teetering at the joint, rocking left, rocking right, then you got a little bit of slab curl that's occurred in that concrete. So to kind of put this into perspective for you, I got a little time lapse photography going on here. This is a damp sponge, a totally saturated sponge, not dripping with water, damp, but it is damp where it's totally 100% saturated, and it's sitting on a piece of plastic laminate countertop. That countertop is acting like a vapor retarder underneath the concrete. So similarly, when this sponge is totally saturated and the water in the sponge can't absorb down because of the plastic laminate countertop, when this sponge tends to dry out, it curls, as you see in the time-lapse photography. You got the edges that are curled up. So to kind of simulate two concrete slabs they're up against each other, we have two sponges that are totally saturated. Okay, again, over a vapor retarder, which in this situation, it's a plastic laminate countertop. But as the water in these sponges dry out, the sponges curl, and this can be compared to two concrete slabs, meaning the center of the concrete slabs or the center of the sponges are in contact with the subbase and the vapor retarder underneath the concrete, but the edges have curled up off the subbase and off the vapor retarder. And if you look at the top joint of the concrete, or the sponges in my photography here, you can see that it's wider at the top due to the curl. Okay, so you have two concrete slabs that have a little bit of curl to them, and you install sheet vinyl over top of them. And what we did here may be kind of hard to see, but we took clear plastic wrap, and it acts like a finished floor covering. And we laid plastic wrap over these curled sponges. And we just let them sit there and we time-lapsed, photography. And what we saw happen, which happens to concrete, is the moisture redistributes throughout the sponge and that curl that was once there relaxes. And now, as you saw in the time-lapse photography, the joints at the top of the slab, or the top of the sponges, if you will, have got closer together as that moisture redistribute and the sponges relax. This happens to concrete. So if you look at this diagram here, you will see a saw cut, cut to roughly 1/4 of the slab depth. You will see a crack at the base of that saw cut. And when the concrete evaporated its water, the concrete shrank and it cracked at the base of that saw cut, just as it's supposed to do, but it experienced curl. And now the two slabs, designated by the saw cut and the crack, they are up off the subbase. Okay, so what's the natural thing to do for any floor covering installer? He'll come in and grind that curled slab so that it's flat, and then they fill it with a patching material, fill the joint with a patching material, and then floor coverings installed. Okay, everything looks great aesthetically. But what really can happen is the moisture redistributes within the concrete, and when it does so, the two concrete slabs relax, and worst case scenario, as that joint at the top that's been filled gets closer together, it can cause failure of the flooring, basically disbonding right at the joint. Okay, bare minimum, what might happen is you extrude the patching material out of the joint, and it creates a bump through the finished flooring. So it looks like a mole run in your finished flooring. Okay. If any of you are flooring contractors, on the call here, by grinding that joint, patching it, installing floor covering, you have done nothing wrong. You have done what you were contracted to do to give a flooring installation that's flat, smooth, and aesthetically pleasing. The problem is a concrete issue. So after you do your installation and we're seeing something at that joint, the concrete is moved, and most likely it's slab curl relaxation, as you see in the pictures here.
Hey, Seth, let me just jump in and just underline something about work requirements and scope of work for the floor covering installer. It is not the responsibility right out of the gate for the floor coverer to affect the parent concrete to essentially grind down those high curls or other imperfections. They can choose to take that on as extra work, but it's not considered floor covering scope. Yeah, so I just wanted to underline that.
No, absolutely. That's an excellent point, because my point to it all, Chris, is as installers, they should raise the red flag. So take your straight edge out to the joints, run the straight edge across the joints to make sure they're not the straight edge isn't teeter-totter. And if it is, then raise the red flag with the general contractor, and we get parties involved to determine the condition and what the remedy may be.
Yeah.
And we'll talk about the remedy here, shortly. But another example, I mean, this is a piece of VCT on concrete. It's a control joint that was patched. This is a cross section. And what happened is, once the flooring was installed, the moisture redistributed, the two concrete slabs relaxed, it extruded the patch from the joint, and it showed through the finished flooring. Here's an example of what that looks like through a piece of vinyl floor covering. As you see the left picture, you see a mole run. The top picture, you have a bubble level, straight edge, and you can see it resting on that mole run. So your job as inspectors or floor covering installers is to raise the red flag. Does all concrete have curl and relax when it's all said and done? No, but it can happen. You have to raise the red flag. In some cases, they may need to inject a grout underneath to fill the void underneath that concrete, so that the concrete can't relax afterwards. And we're talking about drilling holes and pumping a grout in there to try to stabilize everything. But not for you to do or figure out the remedy. Just raise the red flag. Use the straight edge on the joints to see if you got curl.
And Seth, that tendency to curl and relax dissipates as the slab dries. Is that right?
It does. It certainly does.
If you get dry concrete, you've got stable concrete, and then you're able to grind the curl flat without worry about a change of shape afterwards.
Right. But you're into moisture testing and concrete evaluation as well.
Yeah.
Okay, so some of the other moving joints out there, construction joints, expansion joints, isolation joints. Very common that these are recommended to be honored up through the patching leveling material, as well as the finished flooring. In the diagram I show here, there's a piece of backer rod that's in the joint. That joint's honored up through the patching or leveling material, as well as the floor, should be through the floor covering with some sort of elastomeric joint sealant material like a urethane or similar, so that that joint's not only sealed, but any movement that does occur allows that joint to remain sealed. There's different types of floor covering materials out there, transition strips to honor that through the floor covering. You're seeing a tile installation on the left. You're seeing a very large joint cover on the right. Check with your manufacturers on their recommendations on how to honor those joints up through the finish floor covering. I do have a picture of what happens when you don't do that in a future slide here. And I'll circle back to that. But right now we'll move into cracks that are in concrete. Certainly there are cracks in concrete. A couple of things that I can confirm with all of you about concrete. Concrete gets hard, concrete cracks, and the most important thing that I'm going to teach you that none of you probably ever knew this about concrete is nobody's going to steal it. Okay, I will stick with my day job. There's going to be cracks in concrete, and as an installation contractor, you need to patch those cracks, prior to installing flooring. But the thing that you got to keep in mind is just because you patch them today doesn't mean it's never going to move. The crack's never going to move going forward. So yes, it's your job as an installer to patch it, make it smooth, put the flooring down so you don't see anything optically. But if movement does occur, it's going to show through the finished floor covering. And if it's a structural crack, they need to be remediated prior to installing the flooring. So what can happen if you look at the picture on the left? It's a VCT installation that has been repaired twice, and I say that because not only do you see the joint running down the middle of the tile, but you can see that it's a different lot of VCT going down where the joint is in the middle because it's a different color. So you install over a moving joint, everything looks great until the movement happens, and then the flooring installation does not look so good. In the right, you have a hard tile installation, crack in the concrete that was not remediated, and the concrete moved and has thus cracked the finished flooring, the tile. So a couple of different types of cracks that you see out there. In plane, that's where there is a crack in the concrete, but same elevation. But the most concerning would be an out of plane crack, and that's where one side of the crack is higher than the other. That's a dead giveaway of some sort of structural movement just about every time. So any out of plane cracking, by all means, raise the red flag. If you're seeing in plane cracking that's a hairline, that may be one thing. But if you have something that's open like you're seeing in the picture here, then raise the red flag too. Get with the general contractor and talk through with the structural engineer on methods of raise the red flag with them so that they can talk through methods of remediation that can include the installation of finished flooring. So get the GC, the superintendent, project manager involved, structural engineer, and let them come up with a method of remediation. One possibility of repairing cracks would be a stitch application, as you see in the picture here, basically making perpendicular saw cuts across the crack, dropping in, I've seen guys do masonry nails, small rebar, and you use a two-component rigid material such as a two-component epoxy or urethane, and you're basically bonding the crack back together. The masonry, large masonry nail or rebar with the epoxy or urethane is creating a stitch to help repair that concrete. But again, while this is a remedy, as installers, it's really not your job to make the remedy. Raise the red flag, get the GC and the structural engineer involved, and this is or a possibility of a repair method. Now, nothing's ever 100% guarantee, but nonetheless, it's a possibility. I've seen guys use carbon fiber mesh to help stop and resist movement. But if the concrete wants to move, no matter what you do, there's really nothing stopping it. It could crack 4 inches over from where you just made a repair, for that matter.
How deep are those cuts for the stitching? Looks like they're about 1/4 inch or so.
Yeah, it all depends on the material that you're using. You get into something small like you see here, it might be a 1/4 inch or so, but if you get into some of the smaller rebar, they may be a 1/2 inch wide or so, and maybe down down maybe towards 1 inch deep, depending on the width and the thickness of the rebar.
Hmm.
Some of the other cracking that you can see out there that we'll discuss could be from a joint spacing standpoint. We did talk a little bit about curling or warping. We'll show some examples there. Could be inadequate thickness of the concrete, panel shape, the load not being adequately distributed, and sometimes due to misaligned dowels when you're dowing, one concrete pour to another concrete pour. The dowels that they use in both pours that are epoxied into both pours, into the core of both pours, may not be lined up right, and that could contribute to cracking. So, couple of pictures here. Late saw cutting could be an issue. We talked about cracking in concrete due to the shrinkage of concrete, and those control joints that are cut are typically done on day one. Once the concrete has been screeded, floated, and finished, they come back and cut those joints. What happened in the left picture here is a joint that was cut too late and the concrete had already cracked. And on the right is just an example of a really nice deep joint. Looking at the thickness of this joint being 3 inches deep, it's probably concrete that's somewhere around 10 to 12 inches deep. The saw cut needs to be roughly 1/3 to 1/4, I'm sorry, 1/4 to 1/3 of the slab thickness to be able to create a relief break for when the concrete shrinks. So if your saw cut is not at least 1/4 to 1/3 of an inch, 1/3 of the thickness of the slab, then the depth of the saw cut's not good enough, and it's not going to do you any good. So a typical 4-inch slab should have a saw cut that's 1 inch, inch to 1.5 inches, somewhere in that thickness, to allow for a break at the base of that joint. Corner breaks, as you see in the picture here, warehouse application, 4 concrete panels coming together. Curling obviously happened here, and then the concrete slab is not supported underneath there, and we had some sort of heavy point load or rolling load here that caused the break to happen because of the curl or the warping that was experienced here. And then you see the corners break, and the concrete falls back down and is in contact at that point with the sub base. Again, if there's curl that's going on, we raise the red flag. Nobody raised the red flag with the curl. A point load or a rolling load caused breakage, as you see here. Some other concrete cracks that you may see out there could be due to shrinkage or improper jointing or an improper reinforcing detail. The top picture, or the left picture, I should say, we have a joint in the middle top of that picture, and then another concrete slab was poured, and that joint in the adjoining slab, the movement there, caused the concrete to crack in the adjoining pad, as you see in the middle to the bottom part of that left picture. You go to the bottom right picture, that is a crack that's coming off an outside corner of a drainage grate. That crack off the outside corner is called a re-entrant crack. Technically, there should have been a saw cut there coming off the corner in all four corners, because as the concrete dried and cured and dried along both sides of that, you get movement, you get shrinkage movement there, and there should have been a saw cut there. There wasn't, so the concrete created its own saw cut in the form of a crack going in whatever direction it wants it to go. The top picture is a concrete caisson that's there's a caisson that's going down into the earth that's supporting a concrete column, and the concrete slab was poured all the way up to the caisson. There should have been an expansion joint, a black asphaltic expansion joint or isolation joint material installed, separating the concrete slab from the concrete caisson so they can move independently of each other. But the concrete was poured over top, and the concrete caisson supporting the metal column moved and thus cracked the concrete that was poured over top of it. And that ends up being because a joint was not placed there to allow movement of the two materials. Crazing. This is when you have rapid drying of concrete. I mentioned that in one of the early slides, crazing or craze cracks. If you look at the bottom left picture and the top right picture, these are superficial cracks. It could have been high airflow across the surface, sun just drying out the surface water of the concrete, things like that cause a plastic shrinkage to happen right at the surface of the concrete. These are superficial and typically have no effect on anything. But hey, raise the red flag if you see something like that, and let the structural engineer be the one to say that these are superficial cracks. Nothing to worry about.
What's the remedy?
I mean, typically there's really no remedy structurally because they're not moving. But if floor covering's going down, it's a skim coat just to make sure that we're not seeing those optically through the floor covering. But
as long as it's sound and stable.
Wait, say again?
As long as it's sound and stable, no flaking, and is offering up a good bond, then a skim coat, which is typically what, a millimeter thick?
If that, it could be trowel flush to the surface, only placing enough material to hide minor imperfections.
I think there's a big misunderstanding out there in construction that skim coats will at some point level out of tolerance concrete, right? Well, just do 3 skim coats instead of 1. It'll all be good. It's not the case.
Not the case at all. You're absolutely right, Chris. So top picture is a little bit more dramatic crazing that's going on, straight line cracks that start and stop, rapid loss of mixed water in the concrete within the first day of placement. You see cracks like this, again, raise the red flag. Typically, they're just optical cracking, but really the structural engineer has to determine that. It could be as simple as patching with a patching material. In some cases, the structural engineer may want a low viscosity, 2-component rigid epoxy or urethane to be injected into those to help stabilize anything, just to be safe. But it falls back to the engineer, the structural engineer, to make that determination and recommendation. So just raise the red flag. Pop outs, you can see these on occasion, both interior and exterior. In some cases, it's an aggregate material that somehow slipped in that's not supposed to be in there. I'm in Pennsylvania, Western Pennsylvania, and we're a heavy coal area, and sometimes bits of coal get in with aggregate, and it's not supposed to be in there. So when the aggregate gets placed into the concrete, we have bits of coal, and sometimes we'll see these types of pop outs, and you see a little bit of coal right at the base of the conical pop out. I mean, there's other materials that sometimes slip in that shouldn't be in there that can cause pop outs. Certainly, in areas of Pennsylvania and other parts of the US, and to include all over Canada for that matter, the ice melt products that are out there can do some damage. We really shouldn't use traditional rock salt, sodium chloride type materials as an ice melt, because they can damage concrete.
What do you mean by ice melt?
Well, I'm just calling the general material that's used as an ice melt. Like if we have ice, or we're going to expect ice or snow, we broadcast these types of products, sodium chloride or rock salt or calcium chloride, those types of things as an ice melt, if you
I
will,
see.
because it lowers the substrate temperature so that it lowers the freezing temperature so that things can melt. They should be using materials that don't affect concrete, but unfortunately, we see in the States here that they sell regular old rock salt all the time at the big box stores, and that's detrimental to concrete that can cause pop outs. In essence, if you're seeing pop outs like this, interior or exterior, again, raise the red flag. And in some cases, they got to take a core sample to confirm what the cause of the pop out is. We just all know that concrete should not have pop outs like this. So need to raise the flag and confirm what the cause is. And then once that's done, then offer a means for remediation, depending on what the cause is. Blistering. With any type of concrete or mortar material, if the finishing process happens too quickly, you can trap air right at the surface of the concrete that creates a blister. So this is a picture of a concrete slab that has blisters in it. You can see the raised blisters. And it's a function of the troweling of concrete. If we close the surface of fresh concrete before it's hard enough and ready enough to have a steel trowel on it, we can trap air within the surface of the concrete that equates to a void at the surface and a blister when it's all said and done. If you look at a cross section of concrete that has one of these blisters that was an air-filled blister due to finishing it too quickly, you can see that right here. Trapped air at the surface of the concrete, there's a void underneath the surface, and you can see that is slightly raised because there is a void there. So when it comes to placing concrete, it's a touchy feel type thing. It's like, okay, it's not ready, it's not ready, it's not ready, it's not ready. Okay, now it is ready. And it's the concrete contractors that, from experience, know when to get on concrete and other materials at the right time to finish it with a steel trowel. Point being is, if we get on patching materials or concrete materials too quickly after they've been placed, the steel troweling of it can create blisters, as seen in the picture here.
And the correct timing of that wet finishing power troweling process will depend on weather as well as mix design, as
Yep.
all sorts
Everything. Ambient conditions, meaning humidity conditions, temperature, airflow, concrete design, temperature, all those things play into the equation of, when that concrete is ready. It's certainly fluid when it comes down the chute of the concrete truck, or whether it's being pumped and it gets screeded into place. But then the floating and the finishing is really a touchy feel type thing that the concrete finishers are going through. They're touching it, and it's not ready, and it's not ready, and it's not ready, and it's not ready. Okay, now it's ready.
Yeah.
It's a trial and error type thing.
No one shoe fits all. You can't just say, well, leave it for 24 hours and then get on it. Every job's going to be different.
Everything's different. Absolutely. Osmotic blisters. Maybe you guys have heard this term before. It does not happen very often. And there are several things here, three things actually, that need to happen for an osmotic blister to occur. Sometimes you see osmotic blisters in polymer coatings, even in epoxy terrazzo, epoxy coatings. And for this to happen, number one, we need a solvent, and certainly in applications of concrete, that solvent could be water, could be groundwater as the source, possibly could be mixed water if we haven't let the concrete dry enough. We need a solute, and that's basically a soluble organic or inorganic material. And concrete has salts in it. There's natural sodium, potassium, chlorides, sulfates in concrete. They're in there all the time. They're low parts per million. They never hurt anything. They're just in there. But if we have a lot of excessive moisture, sometimes maybe salts are coming from the ground, depending on the application. Maybe they're coming topically based on the use of the area. But if we have salt levels, if we have a water source, and we have a semi-permeable membrane, that is the three things needed for an osmotic cell to develop. And when concrete cures and dries, as all that excess water evaporates out of the concrete, it can leave, what do I want to call it? I could call it like veins in the concrete, if maybe from a descriptive standpoint. As the water's leaving the concrete, evaporating out into the air, it creates microscopically like veins in the concrete. And sometimes the cement paste around the surface of the concrete can be a semi-permeable membrane that allows molecules like water to go through, but not come back down the other way. And if we have a high salt level at the surface of the concrete, if we have this semi-permeable membrane, if we have a water source, liquid water coming up from the bottom, which naturally is intended to dilute salts. So as that liquid water rises to the surface, and you have that semi-permeable membrane at the surface, could be the pore structure, you can get a head of pressure of water at the very surface as it tries to dilute the salts, and it can't go back down into the concrete. And that head pressure can create pressures that reach over 400 PSI. And when you look at the tensile strength of concrete, it's typically 10% of the compressive. Concrete has a compressive strength commonly 3,000 to 4,000. So your tensile strength or integrity of the concrete, the tensile strength is roughly 300 to 400 PSI. And these osmotic cells can create pressures that are over 400 PSI that can cause blisters at the surface of the concrete, fracture in the concrete. I've seen it where they create a blister in a resinous material like epoxy terrazzo or a high build epoxy coating. I mean, these are products that have compressive strengths of 10 and 20,000 PSI, and the force of this osmotic blister can blister a very rigid epoxy material, as seen in the picture here. And you take a drill and drill down through this resinous coating, and you have liquid that pops out of that blister, and it's very alkaline, super high, probably pH of 14 on the pH scale.
So Seth, when you have a high pH or alkaline content at the surface, salts at the surface, those
Yep.
salts are basically drawing up the water. Water is attracted to salt because salts are desiccant, are very, very dry.
Absolutely, that's exactly right.
So this is one of the reasons why we look to control through pH testing the level of salt. If you've got 14, you've got a very high pH level, then you've got potentially this problem coming. Is that how you see it?
That's a possibility. I mean, if we have a high salt content at the surface, that's one component. You need a semi-permeable membrane, which could be the paste, but we also need liquid water. So I'm not talking vapor like, water is a gas. It's literally liquid water, that concrete being 100% saturated. So, do we expect to have a concrete slab 100% saturated with water? We don't. But certainly on a renovation project with no intact vapor retarder from, 20, 30, 40, 50 years ago, then yeah, we could be in a situation where we're totally saturated with groundwater.
And no sign of this problem until you cover it with a floor covering. It doesn't allow
Right.
vapor to pass through it.
Yep, it's absolutely right. And, it's difficult to predict this too, even with just taking a couple of core samples and sending it to a lab. But all three things are needed. The main, certainly there's salts in the concrete. You could have them at the surface, could have the semi-permeable membrane being the cement paste, or maybe contaminants like adhesive residue at the surface of the concrete. But we need the liquid water as the third piece for this to happen.
So puncturing one of those blisters is a risky thing to do.
Well, wait, say it again about the blister.
Puncturing one of those blisters, wear your goggles.
Yeah, wear the goggles. Yeah. There's not. It'll probably squirt out. If you take if you're in a resinous coating like this, you'll need a masonry drill bit to drill through that, and it'll probably squirt out. Wear the goggles, because I don't think you want pH 14 water in your eye. That's not going to feel so good.
No.
Remediation, typically what's done, it's a very laborious process, but it's something that works and has been proven in the industry. But we remove everything down to concrete. The concrete should be tested by a third-party lab to see the levels of salt in like the top 1/8 inch, top 1/4 inch, top 3 millimeters, top 6 millimeters of the concrete, to see what those levels of sodium, potassium, chlorides, and sulfates are. And if we have high levels of any of them, it's very common that the concrete's removed. It could be an 1/8 inch of concrete that's removed. And then what's done is it's reprofiled with a cementitious material that is suitable to be indefinitely damp. So you use a different cementitious material over the surface. It does not have the salts in it, and certainly wouldn't have a semi-permeable membrane. And then you put a moisture control material over top, patch and leveling, put flooring down, etc. And if we still are in a situation where we have that liquid water, coming up, and maybe we still have high salt levels, with that different cementitious material on the surface of the concrete, the water and the salts can flow up into the new leveling material and can move around and can go back down, because there's no semi-permeable membrane in that new material that was placed. So it's a laborious application to remediate osmotic blistering situations, but a proven industry practice.
So there's essentially space for that PSI, that 400 PSI to dissipate.
Well, actually, it won't ever happen, because the water kind of can go up and swim around, and the water and salts can swim around in the new cementitious layer.
Yeah.
And not build up directly underneath the resin material.
Right.
You don't have that head pressure build up, because the semi-permeable membrane is not in that new cementitious layer.
Yeah.
If that makes sense.
And all concrete, correct me if I'm wrong, but all concrete comes highly alkaline, at least 12 on the pH scale.
It does. And then when it starts to cure, and the water is chemically bound and evaporated out, and then the carbon dioxide in the air starts to react with the surface of the concrete will typically carbonate, and it reduces the pH at the surface, typically down to maybe a 9, 10, something like that.
Right. So it just warrants attention being paid to this topic, because it's potentially coming to every job out there that's dealing with new concrete.
Yep.
And that type of flooring.
Yep. Okay, another type of blistering out there is ASR, alkali silica reaction, sometimes referenced as alkali aggregate reaction and near surface alkali reaction. So similar to osmotic blisters, we need things present for ASR, AAR, or NSAR to happen. Number one, you need alkaline moisture. So yes, there's natural salts in the concrete, which are alkaline, but we need the water as a source to realize the high alkalinity of those salts. So you need alkaline water. And something that is not very common in concrete is for this to happen is a reactive aggregate. So there are aggregates that are specified for concrete, ASTM standards. These aggregates have to meet the aggregate standards for concrete, and aggregates are tested for reactivity, and they are not permitted to be used in concrete. You know, we're a manufacturer of patching and leveling materials. We test all of our aggregate by third party to ensure that the sand and aggregates that we're purchasing are not reactive aggregates. But unfortunately, reactive aggregates sometimes slip in. So if we do have reactive aggregates, if we do have liquid water and alkaline water, a reaction can happen with this alkaline water and the aggregate that creates an expansive gel that can also reach PSI over 400 pounds. And that force can cause a pop out in the concrete. If there's no floor covering on the concrete, then there's typically never an issue because any water that's in the concrete just evaporates right out into the air and it never has a chance to react with the aggregate. But as soon as you put something over the concrete, then that water accumulates, you know, right at the aggregate. And if it's alkaline water at the aggregate, that's when the reaction happens. Now, it is a form of a pop out, and I'll tell you this, nobody's going to be able to visually look at a pop out and say, hey, this is ASR or NSAR. Okay, you got to send to a third-party lab and have them test to evaluate that it is ASR. And unfortunately, if it is ASR, it's basically the concrete has cancer. So if there's aggregate at the surface, there's probably aggregate at the middle that's reactive. There's aggregate at the bottom that's reactive. Unless you can be 100% sure that you have remediated all chances of liquid water in that concrete, then there's always that potential for ASR no matter what you do. Even if you reprofile the surface, that reaction could happen, and it could cause a failure in the new material that you put right at the surface of on the surface of the concrete. You know, short of pouring another 4 inches of concrete over the existing concrete and dealing with elevation issues, you can't just put a thin coating over top of this and expect ASR not to occur again. You really need to eliminate the source in this situation, which would be water.
So the solution is to break out the jackhammer?
Yeah, really, unfortunately, or pour a topping slab over top.
Yeah.
It's like the experts in the industry always refer to this situation as the concrete having cancer. What do you do with cancer in situations where it's horrible? You cut the cancer out, cut the concrete out. Not what anybody wants to hear, but nonetheless, you know, you can't correct it just by simply patching over top of it and reinstalling flooring.
You mean Ardex doesn't have a version of chemotherapy for this?
Yeah, really, I know. Need it. Just a picture here. I mean, you saw the previous picture, but this is petrographic analysis of concrete and a third-party lab that confirmed that the material above the arrows, the red arrows, is a gel-filled cracking, alkali silica reaction gel that filled the crack once the reaction and the crack happened. Another term you'll see in the industry is spalling, and this is a fracture in horizontal and vertical concrete delivered by a massive blow. So you look at the top right corner, that's a corner of a stair in some capacity. Some sort of direct blow caused that concrete to fracture, and that's called a spall. That's the true definition of a spall. And for that application, it'd be some sort of structural repair material once that's cleaned up and reformed, structural repair product to repair that stair nosing. The vertical wall there, same situation, some sort of massive blow caused a fracture, and some sort of structural repair product to fix that vertical application. Scaling is another term when you lose the entire surface of the concrete. This is very common when air-induced concrete is used in an interior application where they steel trowel it. So they typically entrain air into concrete for exterior applications in freezing environments so that there ends up being voids in the concrete so that when that concrete gets saturated in the wintertime when water can freeze, the water goes into these voids created by the air bubbles and expands and doesn't affect the concrete. They entrain air maybe, I don't know, it could be 8%, 10% air for exterior applications so that you have all these voids in cured concrete for water to go and freeze and expand and not affect the concrete. Unfortunately, it sometimes gets used inside and gets steel troweled, and it should never be steel troweled. Because what happens is if you steel trowel air entrained concrete, you'll create a layer of air bubbles directly beneath the surface. And when everything is cured out, you got these layer of air voids directly below the concrete. And any type of force will break that weak layer of air voids, and you get the whole surface that scales off like you see in the picture here. So scaling is a term when you lose the entire surface of the concrete, and steel troweling air entrained concrete can cause that. Remedies is basically remove everything down to solid concrete and then repatch or level as necessary. Dusting is another situation caused by finishing the concrete too early. And this goes back to the kind of the air bubble issue. If we get on concrete too early with a steel trowel, we can blister it. But if we also get on it too early and work the surface, we can bring too much mixed water, concrete mixed water to the surface, and we basically overwater the surface of the concrete. So if you have concrete that's cured and it's dusting, you rub your finger on it, and you got dust on it, it's very common that it's a result of troweling the concrete too early. That's dusting. The fix is very easy. You just mechanically clean the weak surface, get to the hard stuff, and then patch or level as necessary. So, you rub your finger across the surface and you got dust on it. That's the term dusting.
I heard gas burning heaters such as propane exhausting carbon dioxide that carbon dioxide will interact with the fresh concrete surface and produce dust. And if you wonder why I'm sweeping up, there's just more dust coming, and you're burning propane, that's a possible cause.
Yeah, no, you're absolutely right. You got fresh concrete, you got your fossil fuel, whatever, heaters, machines, whatever it might be, and that carbon monoxide exhaust can react with the concrete, absolutely creates a very weak surface that ends up being dusty. It's a great point, Chris. But the fix is also easy too. Mechanically clean down to the hard stuff, and then patch or level as necessary. Just raise the red flag when you see this. We all know, good solid concrete. Hopefully is my camera still on, Chris?
Yeah, you're good.
You see this key?
I lift it up a bit. Yeah.
Yeah, it's not much of a key because this is what I've been scratching concrete with for 30 plus years. And concrete's hard. I leave a metal burn mark on the surface of the concrete because I'm basically wearing the key away. But if I'm scratching into the concrete, that throws up a red flag. What am I dealing with here? Something that's weak. All right, let's go figure out why it's weak and what we're going to do to fix it.
That key should be deemed an official soft concrete testing tool.
That's my ASTM key.
Exactly. There's quite a bit of controversy when you start scratching the concrete. Well, that's not a real test. What are you talking about?
Yep.
But if you can make a mark in the concrete, something's not right. As you say, raise the flag.
Raise the flag. We all know what concrete is. Go out to your driveway, sidewalk, next project you're on, you're not gouging into it. It's a hard material.
Yeah.
Yep. Efflorescence. Okay, that is a very big word. Not to be confused with effervescence. I wish I had, there's another one where I wish I had $5 every time I had somebody say I got an effervescence problem with my concrete. I think I could have retired 20 years ago. I had one guy say he had a phosphorescence problem with his concrete. We're not talking about, the bubbly. We're not talking about glowing rocks or anything fluorescent like that. Efflorescence, this is a process where excessive moisture takes the natural salts and drives them to the surface. Pretty extreme situations, as you see here. The right picture is salt formation through VCT, excessive moisture driving the natural salts of the concrete, and you got white salt formation at the surface. The left picture is pulling back some a vinyl material, and we're left with whitish residue on the underside, and that's natural salts from the concrete, indicative of a moisture problem. That process of water taking the salts to the surface is called efflorescence. So yes, the efflorescence is a problem because it's a contaminant, cause a bond problem, but it's a result of excessive moisture. So yes, we got to remove the contamination, the salts, but we also got to address the moisture issue too, that is the cause of the efflorescence.
It's interesting when you pull up tile, when there's an efflorescence problem that exists, you pull up the tile and you can see the trace of salts all the way around the outside of the tile, where I guess the moisture vapor can escape through the space, the joint.
Yeah, that's the path of least resistance. Absolutely.
So at that point where it's escaping, it's depositing the salt, I guess, on the surface and leaving that that mark around the outside of the tile.
Yep, absolutely. Okay, condensation. That's another situation that can happen out on site. This is a typical dew point chart, and it's pretty simple. If you gather specific information about a project, you can see whether you're close to dew point or not. If we take your ambient humidity, your ambient temperature, and the substrate temperature at the surface, you can quickly see how close or how far you are away from dew point by simply going, using a chart like you see here and plugging in the values. I don't know if you can see my cursor, maybe you don't, but
We can.
you can? Okay, so just for example, for 70 degrees temperature and 70 and 50, we'll do 70 and 50 because those are two common values. So 70 degrees temperature, 50 to 50% ambient humidity. In order for condensation to occur, I need a substrate temperature of like 50 degrees. So you're very far away from dew point if we're in an acclimated space, because we're acclimated and we're at 70 and 50, the chances of the concrete slab being at 50 degrees are probably slim to none. But when you're not acclimated, that's when you can fight with condensation. I'll just give you a quick example here. I was on a project in the fall in Pennsylvania, retail store renovation. We get warm days in Pennsylvania in September and October. We get rain, and we had one of those cool days that all of a sudden we got a warm rain come through, and it was warm in the afternoon and didn't have the storefront on, and basically all this warm, moist air moved into the storefront, and the concrete slab was cool. The windows were cool, and basically it was raining in there. With that warm, moist air into the building and the concrete slab being cold and the windows being cold, we had water running down the windows and water formation on the concrete. So it's like, hey guys, put the storefront on, turn the HVAC on. We got to get out of a dew point situation. So it's quick. It's very easy for you guys to see how close or how far you are away from dew point. You go down to a local big box store, buy a hygrometer for $20. It does ambient temperature and humidity, and then you do your substrate temperature, and you can see exactly where you are in reference to dew point on the substrate. And Typically, manufacturers want to be at least 5 degrees away from dew point and rising.
You can
So
you can
we want-
Google dew point calculator and you'll get some you'll get the calculation device. All you have to do is at that point put in the air temperature and the relative humidity, and the Google will tell you what the dew point is. Very useful.
Yep, absolutely. All right, pH. Anybody know what pH stands for? And I screwed my whole joke up here because I already fast forwarded to the slide. No, it's not Planet Hollywood. Oh man, I really got to stick with my day job here. Gee whiz, no comedian work for me. pH is the power of hydrogen or potential of hydrogen. We're measuring hydrogen ion activity and indicates the level of acidity or alkalinity. So looking at a pH scale, it goes from 0 to 14, 7 being neutral. Okay, everything left of 7 or lower than 7 is acidic. Everything right of 7 all the way up to 14 is alkaline. And the thing that I want you to understand is that this is a logarithmic scale. So yes, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But as you go, one measurement, 7 to 8, it's 10 times the alkalinity to go from 7 to 8, or going, when you go from 7 to 6, it's 10 times more acidic going from 7 to 6. 7 to 9 is 100 times more alkaline. 7 to 10 is 1,000 times more alkaline. Okay, it's a logarithmic scale. Just to put things into perspective here, common materials that have pHs. Our blood in our system is neutral. Pure water is a neutral pH. Certainly, battery acid is extremely acidic. The hydrochloric acid in our stomach, very acidic. Vinegar materials, Coke, Pepsi, very acidic. On the other end of the scale, drain cleaner and bleach, very alkaline. Ammonia, stuff like that, very alkaline. Different materials there. When we look at ourselves just from a typical chemistry standpoint, when we have an upset stomach and we have the acids burning our throat, we have heartburn. What do we use? We use Tums. And I don't know if you ever looked at the back label of Tums, but you're chewing on a piece of calcium chloride, which is basically limestone. So every time you eat a Tums or similar, just know that you're eating a piece of limestone.
That's called milk of magnesia.
There you go. Yep.
Mm.
So anything that says now I'm forgetting what. I just lost my thought on what's on the back of what's in Tums anyhow. Calcium carbonate. So could not think of that. So it's basically limestone. So when you're eating materials like that to settle your stomach, you're basically eating limestone.
Mm.
And the reason being is limestone is very alkaline, and your stomach acid is very acidic. So they're offsetting each other. We're neutralizing the stomach acid with the Tums or similar, or milk of magnesia, for example. Hopefully that makes sense.
Yeah.
Typical adhesives tolerate 9 to 10 on the pH scale. Present day, you'll see ones that go up to 11, even 12 on the pH scale. Fresh concrete is around 12 to 13. But what happens is, and as I said this earlier, is concrete carbonates when the carbon dioxide in the air reacts with the concrete. It'll carbonate and it'll drop the pH down a little bit lower than where it is when it's fresh. So it's suitable for adhesives in flooring. So from a testing standpoint, it's pretty simple. You're cleaning the surface, using distilled or deionized water, putting a 1-inch puddle You could use a pH strip in the puddle of water, and then you're reading that to see what your pH is. Brand new ASTM standard that was released within the past year, something like that, is 3441, which is a guide for measuring pH underneath resilient floorings. Just a standard that kind of gives you the directions on how to conduct that pH test.
So if my adhesive wants a pH of 7 or 8, and I'm testing at 12, what do I do?
Call the adhesive manufacturer and get their recommendations on what to do. If the pH is too high, they may tell you we got to moisture remediate because this is what we have, or maybe they have a material that gets applied to the surface first as a neutralizer. But yeah, call the flooring adhesive manufacturer and let them detail what needs to be done in that situation. Fly ash, and we're almost there, guys. I know we're running over a little bit here, but fly ash is a byproduct. It's a byproduct from burning coal in power plants, and it's used as a supplementary cementing material in concrete. I don't want to get terribly technical with you, but I do want to kind of explain the chemistry a little bit here, just so you understand why fly ash is used in concrete. Number one, it's considered a green material because we're using, a byproduct into another product. But from a pure chemistry standpoint, you have Portland cement and water in concrete. Those two react together to create the binder that binds the sand and the stone in concrete. Chemically, that Portland reacting with water creates a material, the main binder in concrete, that's called calcium silicate hydrate. If you would chemically analyze concrete, the binder, the paste that's holding all that stone and sand together is calcium silicate hydrate. The byproduct of that chemistry of the water and the cement reactant produces a material in concrete called calcium hydroxide, or like free lime in concrete. And what the fly ash is doing, once the cement and water react and create the byproduct called calcium hydroxide, the fly ash that's in the concrete reacts with that lime in the concrete, that byproduct, and it creates additional calcium silicate hydrate. So from a pure chemistry standpoint, fly ash is used to densify concrete. It creates a tighter, denser mix. But it's very critical on how much fly ash is added into concrete, because it depends on how much of the calcium hydroxide is in there as a result of the concrete's chemistry. Okay. And unfortunately, I've seen some crazy amounts of fly ash put into concrete, trying to get projects to be LEED, certified and green. And putting too much fly ash in concrete can be a detriment. I just want to tell you some of the things here that can happen. But from your standpoint, it's if you're aware of fly ash in concrete, I just want you to be aware, and certainly you want to evaluate the concrete, scratch it to see if there's any deficiency. But typically, at a rate of about 15% by weight, is pretty common that manufacturers, are good with that amount of fly ash in concrete and not causing problem for patching and leveling materials, or adhesives and floor covering, things like that. But the problem is that most people think that the concrete is like normal concrete, very absorbent. But what can happen is when you add fly ash to concrete, it makes the concrete more dense and less absorbent. So the absorbency standard from ASTM is F3191. It's quite simply dropping, water on the surface of materials, letting it sit there for, a minute and evaluating the absorbency. Does it soak in and change the color? Or does it just sit there as a puddle? It doesn't change the color. And the point being is added fly ash to concrete can make the concrete less absorbent. So from a flooring adhesive standpoint, it may mean a different adhesive. It may mean a different notch trowel for the adhesive you were going to use, maybe a smaller notch. it may mean a longer open time for that adhesive. Okay, but when you're testing for absorbency and seeing that it's not absorbent, then check with your adhesive manufacturers to see what their recommendations are. Some of them, with the waterborne adhesives, they go with a smaller notch trowel, longer open time. Some may want a blotter layer of a porous cementitious material. Check with your adhesive and flooring manufacturers. Couple of things that can happen when we have too much fly ash in concrete. You get into levels like 30 and 40%. You could have unreactive fly ash in the concrete because there's not enough free lime in there for the chemistry to happen. It could equate to very slow strength development, and it could also equate to a weak surface. So again, not that I expect you to be able to identify, or should any of us be able to identify fly ash in concrete just by doing a visual, but get out there on the concrete and evaluate it, scratch it, cut it, do some absorbency tests so you know what we're dealing with from an absorbency standpoint, and an integrity standpoint, and you raise the red flag, as necessary. Last slide. In some cases, we need to harvest samples. And I want to give you a couple of ideas here on what should be done for third-party lab evaluation. Okay, this is a project that had some small blisters in it, and we wanted to send core samples to a third-party lab so that they could evaluate it. And the whole idea is we wanted to be able to give them a totally intact system so that they can peel back the onion, basically, and then evaluate and conduct a petrographic analysis to confirm the cause of the condition. So you can see in the first picture, top left, that I drew circles on where the blisters were as for identification reasons. So the lab knows exactly where the blister was. And sometimes you need reflection of light. Sometimes you need a flashlight or maybe your phone flashlight to try to see that. But you want to circle the areas on the surface so that the lab can identify what you're seeing on site. And then we drew the perimeter. We have a diamond hole saw for cutting the core. We traced the perimeter of the diamond hole saw and then actually measured the thickness of the diamonds and then drew an inner circle and scribed the flooring and removed the flooring so that the diamond hole saw could sit directly on the substrate beneath the flooring. That way, we're not tearing the flooring off when we're trying to harvest the core sample with the diamond hole saw. So that's a critical piece of having the complete assembly intact. The other critical piece is not wet coring. It's a dry core. Water introduces a variable. Most guys that cut concrete with diamond hole saws, they want a wet core. And the problem is you introduce a variable. So you can certainly dry cut. And actually, if we're worried about crystalline silica, I mean, there's attachments that go on the diamond hole saws, a vac attachment that you can hook up to a HEPA vac system so that we can operate without creating dust. But we want to dry cut so that ultimately we can harvest that core sample that has a complete assembly, the complete flooring assembly intact for the lab to peel back layer by layer like you're peeling back an onion. As soon as we harvest the core sample, we wrap it in a paper towel, wrap it in aluminum foil, and then put it in a place in a Ziploc bag and send it off to the lab. Typically do a minimum of 3 cores is my recommendation. 1 core could be an anomaly. 2 cores could have 1 anomaly, and you only have 1 good data point. So we should do a minimum of 3 cores. We typically use 3x5 cards to write what's going on, where this is from, where the room is, stuff like that, what the job name is, label as core 1, core 2, core 3, take pictures with the 3x5 cards, things like that, so it's well documented. But the key things here is to, in situations like this with resilient flooring, scribe the flooring off so we're not spinning it off during the harvesting process, and dry cut core the samples. Hopefully that makes sense. And I appreciate the time here this afternoon, I went a little bit long. I greatly apologize for that. But I certainly open it up to any questions that anybody has at this point.
Great information, Seth. Thank you. Yes, let's see if any questions come in. Thought I'd let you roll because the content is so dense and good, and we're recording this so everybody can watch it at their leisure later on if they go to our website, nfca.ca, and just click on free resources, and there's our video library with this and many other presentations. Yeah, so if no questions are coming through, then I think you're off the hook there, Mr. Pevarnik.
Well,
Sorry, sorry to interrupt. I just had one. I can't seem to get through the chat, but it's Dennis Glaze, and I just want to know, how do curing agents affect the pH level or moisture migration in concrete?
Yeah, it's a great question. So from a pH standpoint, the typical curing compound that's placed on the concrete will end up yielding a neutral pH. So from a testing standpoint, that's a pH testing standpoint. That's a way to confirm whether there's something on the. That's one way to help confirm whether there's something on the surface of the concrete or not. I would not expect if I was testing actual concrete to get a neutral reading of that concrete. I would expect somewhere maybe around a 9 or a 10. The other thing you could do with that curing compound, take your knife out, and while a curing compound may be clear, when you shave it or scrape it, optically it looks white. So it ends up creating a dust if you take your knife and kind of scrape it off, and that dust will look white under a magnifying glass. Any type of clear coating, that's kind of typical. If you're scraping concrete, you're going to create a dust that actually kind of looks a little bit gray. It looks different. And you can certainly practice that just by applying any type of clear coating onto something and letting it cure and dry and, scraping it off and see what it looks like. From a moisture standpoint, if there's a curing compound, on the concrete and you were doing calcium chloride testing, then that's going to affect the moisture that evaporates out of the concrete and may give you a false reading. It may potentially, with any surface probe meters too, give you maybe a false reading potentially, but check with those manufacturers. From an RH standpoint, it would not, RH testing standpoint, that curing compound on the surface wouldn't affect the RH reading, because you're drilling down into the core of the concrete and testing, moisture within the concrete. Hope that helps and hope that makes sense.
Oh, that's great. Thank you.
Yep, my pleasure.
Okay, anybody else with a question? Nope, I think we'll stop the recording and leave it at that. Thank you again, Seth.